an extremely spaces in extreme bench. But I want to talk about some recent developments there that you could kind of compare with this mining bitcoins, mining cryptocurrencies, because there you do something exponentially difficult as a firm. And it might be that building perfect hedge fund is also difficult. We don't know. And we'll talk a little bit about that, but it's just the motivation for doing this mining. So, what's perfect hedge fund? For minimum, we have a static set of elements from the firm. So we want a data structure that specifies the function that allows us to map a set of keys injected bijected the first n integer was not minimal perfect, maybe the range is a little bit. So for the minimal perfect hash function in KFS, there's a no lower bound, information theoretically, that you need at least log e bits per element, so about 1.44 bits per element. And notice that this is usually much smaller than just storage that gives us a very basic data. And yeah, what we would like is a data structure where we get near to this minimal space, but at a constant time speed, ideally in linear constant. And there are lots of applications. We already mentioned databases. You can, for example, use it for aesthetic space, or for management data structure, or updates to the previous data structure, or maybe as a replacement for pointers. Okay, for long pointer, but just quite and this talk will somehow move back and forth on a scale between doing some unstructured brute force and more structured structured get somehow the best of both. So there's a very simple brute force argument for computing. You look at the sequence of hash functions. There's one hash function that has an additional C parameter that we can iterate one to two, right? And say that is usually failed. It's usually not a particular field, right? So this is very polite. They don't want to make. We try not to see. I know we are able to pull it, but here the third C gives us accidentally. So a brute force way is just that you try to stumble over and then the representation of the hash function right? So this turns out from the space point of this is up to maybe 1 big of it. But of course, the bad news is the exponential construction time and probably also something like linear QE time. For large linear number of bits that we always take. Right? And I will come back to this solution space. Where is the set of all functions? An element is the number of functions. And the blocks here are the relatively small number of perfect hash functions. Right? And here they're just perfect. Right? So if that would be the only way to build perfect hash functions, that would be an ideal way to work, right? But don't know, can we do faster? So keep that right, and I will show you some. So how much time do I have?
You have like 25 minutes.
Yeah.
Then give me 5 minutes.
So let's try to move a little bit more to the practical side from brute force. An obvious idea is to say, oh, maybe we can use it for small subform. And the question is, how do you break your problem of building one large perfect hash function into the problem of building many small. And an interesting result that let us obtain was basically they combined ways of breaking. Once first you randomly hash the bucket. And you can store prefix sums of the bucket. And that basically reduces the problem by the perfect hash function. Yes, because when you evaluate the hash function for the bucket, your element is mapped to and add the prefix sum. And then if you use a standard compression technique for FDR coding, you can do that with that way. So like you need to consider that. These buckets need to be fairly large. So you further break things down in another brute force way. Now you are looking not for perfect hash function style, but only for splitting hash function. So, for example, for splitting hash function, there's a one bit hash function, one bit of force. And look whether accidentally this splits the data into equal size or whatever kind of balance you want. And then you do it in a very systematic way so that the way you split depends only on the size of the bucket. When you don't really need to store the trees and pellets, that you can make the computer of that. And that you just store the seed for the splitting hash function. And then you have to use the problem small of bounded clump that works on the size. Then you would move forward from this. And so all of this is standard techniques for compressed data structure. And then if you do it the right way, you have your goal, you are have to use information theoretically only in a constant number of bits per node. And if you make the deep start, that means you have to merging to state. But of course, the running time will be exponential in the period of a really fast process, but it's all come out from. So when we looked at several ways now to make this fast, and one general approach here can be seen with the limit. What if we sample not individual functions, but like subspaces? Where in each of subspaces you can efficiently for perfectly. And a very small subspace we can get by what we call the basic fitting. So what we do is we have a splitting hash function with one bit again that fits our leading part. And no, it doesn't really matter how it is. And we ask ourselves, okay, one of them individually injected, and it's a good two-bit pattern that describes basically how elements connect together by boring them. Do we overall get a perfect aspect from UDCO? One place is not used at all, and there's a little here, so that isn't good. But we can take a large data space of additional hash functions by rotating the second part in L ways. So we see all don't work, but then by rotating it by two pieces, we get a perfect. Right? And then we can do in a bit parallel way, and we can even use lookup tables to do by all rotation functions. So we save a factor of L in running time of our construction, and we can prove that this way of constructing hash functions out of a random hash function is almost as information theoretically as doing it brute force. And what I forget to say is also the splitting here, they prove that it's also almost optimal function number of the use of the splitting. So building a propagation of splitting stuff before is almost as good as the report for the entire thing. And he proved a similar thing for the rotation. And now you may wonder why is this as a parallel concept, right? I think perfect hashing is an interesting complicated topic. Parallelism is interesting, but not the most, I think that so how do you parallelize this construction? One of the interesting things is that you can parallelize on multiple levels. That is what to really use your hardware. So in this case, we are using bit parallelism, for example, for rotating and putting things together. Single instruction multiple data parallelism, where each lane of an SIMD register has a different hash function. And of course, you can use multi-threading on the CPU. It gets even more interesting on the CPU, where we have threads trying different keys. We also still have bit parallelism. Groups of threads work in different key nodes, but we have a grid of groups that calculate a parallel on keys with the same phase. And then we can use the next layer of parallelism for queue, calculate different key phases. And it's important for using the immense parallelism offered by a CPU to work on different levels at the same time in order to have a massive amount of parallelism. I will later show you some of the results. So now let's move to the other end of this thing. Structured search, highly structured search, hopefully linear time directly. So in this image here, that corresponds to sampling a very large region of our solution space. And the two properties we want to be able to track all the solutions here in polynomial or maybe linear time, in not in the number of functions here that will be and maybe with high probability it contains the direction. Right? And there's a way to do that with compressed data structure, they call it static function or people, where we can basically store data associated with it without actually storing it. So there are data structures that do that for K with T, so K and bit of little. Right? We basically do it by having 2 to the K hash function. And for each element, we store in a retrieval data structure this hash function. Right? And solving that problem can be done in polynomial time, basically using perfect matching in a random graph. Or for those of you who know who has tables, that's basically the static version of building a and actually for random graphs, that can be done in the image. That's also cool. Yeah, we store the static function here. So what in this example is on the theta of the horizontal 0 hash function, the these are the circle. So what do we get out of this? If we store a single bit, we know from random graphs you can the graph that we need a range of twice the range we would like to have. But we store only one bit, so that's the information that is found. But at the time we choose 2 bits, we still need a larger range, but it's close to n, something like 0.4% larger range than the optimal. And there's a trick basically to clear such a non-minimal hash function that is relatively little space, and also on average little. And overall, that gives us minimal perfect hash function with about 2.15. So it's pretty close to 1.44, but not quite there. So let's see, can we move further to the unstructured in reduced space? So for thick hash, we did a paper that with messy, we don't decide on 1, 2, or 3 bits, but using big. We also partition our hash functions into many. and for each piece we allow an insight. And that gives us slightly less space than the simple space. We get to about 2 bits per piece with similar construction time and similar create time. And let's move a little bit closer to that at our top hand. So here what we do is, in a sense, we do sequence with a single bit, and we do this retrieval with piecewise based on a method. So what we have now is we sample a space of an exponential number of choices, but actually it's not big enough to usually contain a solution. So we have to sample many of spaces, but it turns out much less than the simple range. As I said, basically what sample of the single bit retrieval thing means that for each choice, you can model that as a graph, right? Our range is the node of the graph, and when we have an edge that connects to choices, yes. And now we can think about this in a graph theoretical way. And yeah, what you want to do basically, you want to orient this graph so that each of these edges points to one side, and you want that the vertices have only do one point, and then it corresponds obviously to a representation. And then you would just store one bit telling us the orientation of these edges. Yes, and we have seen here, yes, that works, but only if you double your range. But you want to have range 1 to n, not 1 to p. And the kind of surprising thing here is we do it anyway. Okay? So we massively overload QS basically. And then try many things. And it did sometimes work. And then the interesting question is why without this why is this interesting? So I will first tell you about this. And then you will see the success probability that this area is almost optimal. So the orientability check is very simple. So we have this graph, and you see any guess whether this thing is oriented? So if you see this component here, it has 4 nodes and 5 edges. There's no way to orient them to get it. So basically, it's easy to see that a graph is orientable if there's only each of its components has no more edges, and that's what we also call a pseudo. And that can be easily done in linear time by computing connected components. But the interesting thing about this is that by the single linear time computation, takes 2 to the n different scales of our repeated vector. So the time takes an exponential number of potentials. And that's what speeds up things compared to plain brute force. So let's think about the success probability of if you sample a random graph for orientation. The overall number of times is n to the 2n, because for each of the n, you can choose 2 values, right? And taking this formula tells us that the n to the n minus 2 labeled t with n. So we can choose any of the labeled t for our n minus 1 or n minus 1 average. We just pick the first n minus 1 average. And for now, we leave out the last one. An edge in an n node graph. And then the number of ways to build n node trees out of that is n. We don't care about the order generated enters, so that gives us another n minus one obvious possibility. And also we don't care in which order the endpoints are generated. That gives us another to the n minus one probability. And then finally, for the last L, we can do whatever we want. Make a field figure. So that's underestimate of success probability that looks complicated, but it can be simplified to n factorial over n squared, which is the success probability of the two forces times 2 to the n minus 1 over. So we are almost have an almost 2 to the n times higher success probability than if that figure. And that also translates to analogous basis because for this exponential transfer method, we need only also n less bits. Of course, these n bits we again need for the receiver data structure, but overall is that we have n log e bits basically just to option space for this pocket. The practical bad news here is that these orientability checks are orders of magnitude lower than that checking that are single function. So in our initial implementation, that was vastly slower, particularly. But the point is, we have to check only very few things for orientability. To put in a simple filter, in that case, by just checking whether all the values of the range are and the success probability for the filter is just 0.84 here. So the majority of the running time, the majority of the people will already be eliminated by the filter, so that you have a diminishing fraction of computations that actually of each direction have even more complicated. And that makes stochastic effects. Further proof that the bipartite stochastic will be again split into half, building mappings for both of them, and then looking at all combinations, and also having filters there. But due to time, I don't want to go into the details, but we check that plain brute force needs about 2 to the 7 times of virus. Stochastic is about 1.26, and with this bipartite stochastic, we have it down to 1.1. Okay. So we are still exponential in the input size, but with a much smaller basis, and that allows us to solve smaller base, larger base cases, like 100, 120. We haven't implemented this yet, but we can also do stochastic. But it's important that we use the filter, and this would be some kind of hybrid implementation. That validating edge functions and running the filter would work on the CPU, and the few surviving candidates would possibly better be checked by the strong small fraction. So let's look at complete experimental data. And here I'm showing the trade-off between space per element, x to the y axis is 1.4 bit, and construction. And there are lots of methods. One that the when is the whole phase one and several others. And what we see is that the currently most space efficient constructions work on bipartite at least 50%. Okay. Then lane sockets, thing with some rotation sitting or inside, then the yellow line, and then surprisingly comes an efficient Rex split variant that uses SEM variant. So this is all sequential code, but here the same variant. So the surprising thing is that this Rex split that was somehow defined for having no construction in a very low state now turns out to be the highest throughput presentation function that we know. if you allow a bit more space. That's because then you can use very small lead size. Everything around it doesn't take lead size. So that's somewhat surprising actually. And then we have lots of other things that are all dominated. It's all vector variants. But we have to be a bit careful because all the vector variants have quite high key time. So if you look at the trade-off between space and key time, in the lower left corner, we have all these vector variants. But a much faster approach is this spatial thing. And I don't have a lot of time saying that. But basically, brute force again, with the difference that we map elements to buckets, and then each bucket gets sorted. So we don't have an individual for the element, but for the bucket. And then these buckets share some subrange of your head function. So the first bucket may be mapped here, the second one would collide something here, and so on. We do it in a greedy way, but it's still kind of brute force and between buckets, and you can take proof that this is also the property space, but in practice it takes a bit more bits. There's a proof that by using non-uniform bucket sizes in a kind of optimal way, but I don't want to go into details because I don't want to. Exactly what we implemented where again we use many levels of parallelism, and one interesting detail where that I could go back to my diploma students, actually using a technique from 1960 or to emulate MIMD parallelism on FM, so where you would do the stacking of distance in an asynchronous way, although you are computing on a synchronous data. And that was like 62 times faster than the underlying. So, to conclude, we have shown that there's a trade-off between space force and linear timeline on the space. But the parallel engineering to get kind of the data of world, we could demonstrate how to do that parallel. And there's, I think, only the beginning of several others. So the obvious flows that are presented at the end combined. Okay, that's idea to first practice. The picture implementation of software we have done. And the important view, the interesting theoretical test for me is as an engineer, especially how close can you get to optimal state of construction time to field? And I think you can get good things. One approach might be to use data structures in the structure. So that it's fine to use exponential search spaces. You can just use the lookup table to look up. But the way to do that in this case is not good. On the other hand, you could look at how to really use perfect functions that you really say minimum space of one bit. This is then probably exponential. And practically it might be relevant to go back to this case that you have a bit more space, like 2 to 8 bits, but then very fast, very fast. Right? If there's not done space. Thank you very much. Like a lot of for technique space. Yeah, it's 2 bits, right? So you have 1.4 for everything, and it's like 6 the n bits for the receiver and 0.5 Okay, cool. Thanks.
We talked about simulating a view and security. Talk a little bit more about this.
Yes, okay. So in this case, it's very simple, right? In a segmental algorithm, you would have one thread, taking one key, right? And in this application, take one key to have the map the root from 1 to n, mapping the element to your name and checking whether this thing is already on. And as soon as you find an occupied space, you can break the first one and go to the next. And the nice thing here, of course, is that you just have put in a little computation that increments the key, and then everything else is the same. And then it's very easy to fit basically the next subtask or the next iteration of the whole one if you want. So the single classification. But actually there's a whole theory about how to emulate arbitrary MIME programs as I and it's relatively obvious that you always use only constant text. And the first thing for the fix for machines where the instruction there's a problem about actually stored on a disk, putting two random effects to a program space. And then it was obvious that you had only a single loop. We call that the computer I wrote. And then there were actually two papers that discussed how to still do arbitrary control stuff. Then in my diploma thesis, I had an SIM with 15,000 processors. And I actually wanted to do something quite complicated, and it turned out it was complicated.
That's interesting to hear. Sorry.